Ever wondered how AI models like GPT or BERT actually process language? It's not magic. It's a complex interplay of mathematical structures, optimization techniques, and architectural innovations. Today, we're diving deep into the technical heart of modern neural networks, breaking down how they learn, adapt, and make predictions at a level that'll challenge your understanding of machine learning. Let's start with the basics. At their core, neural networks are computational graphs composed of layers, neurons, and activation functions. Each neuron applies a weighted sum to its inputs, passes the result through a nonlinear activation, like RNN or sigmoid, and propagates the output. But here's where it gets interesting. The weights aren't arbitrary. They're parameters that the model adjusts during training to minimize a loss function, which measures how far predictions deviate from reality. Consider a simple feed-forward network. Input features pass through hidden layers, where each neuron's output is a function of its inputs and weights. The final layer produces the prediction. But this is just the skeleton. Modern architectures add layers of complexity, like convolutional operations or attention mechanisms, to capture patterns more efficiently. Now, how do these models learn? The answer lies in backpropagation and gradient descent. During training, the model computes the loss, then propagates this error backward through the network to calculate gradients. These gradients tell us how much each weight contributed to the error, allowing us to update them using optimization algorithms like ADAM or SGD. But here's the catch. Gradients can vanish or explode in deep networks, making training unstable. Techniques like batch normalization, residual connections, and careful weight initialization, e.g., he or Xavier, mitigate this. And let's not forget the learning rate, a hyperparameter that balances how aggressively the model updates its weights. Too high and it overshoots the optimal solution, too low, and training becomes painfully slow. Let's shift to one of the most revolutionary concepts, attention. Traditional models treated all input elements equally, but attention allows the model to focus on relevant parts. For example, in a transformer, the self-attention mechanism computes a weighted sum of all input elements, where the weights represent their importance for the current task. This isn't just theoretical. The scale-dot-product attention formula, QKT/2DK, captures relationships between queries, keys, and values. By stacking these mechanisms across multiple heads, transformers like BERT or GPT-3 achieve state-of-the-art performance. It's like giving the model a spotlight to highlight critical information, rather than scanning the entire scene blindly. Recurrent neural networks, RNNs, were a breakthrough for sequential data, but they struggled with long-term dependencies. LSTMs and GRUs introduced memory cells to retain information over time, yet they're still limited by sequential processing. Enter transformers, which replace recurrence with self-attention, enabling parallel computation and capturing global dependencies. Transformers also rely on positional encodings to inject sequence information, since the model itself has no inherent sense of order. These encodings, often sinusoidal functions, allow the model to distinguish between tokens based on their position. This design not only scales better, but also underpins the success of large language models. So what's next? Researchers are pushing boundaries with sparse attention, efficient quantization, and hybrid architectures that combine the strengths of CNNs and transformers. The goal? To build models that are faster, more interpretable, and capable of handling multimodal data, text, images, audio, all at once. Understanding these concepts isn't just for researchers. It's for anyone who wants to grasp how AI shapes our world. If you're curious about the math behind the magic, subscribe for more deep dives into the algorithms driving the future. And drop a comment. What AI topic would you like us to tackle next? Let's keep the conversation going. Thanks for watching. If you learned something new today, hit that like button and share this video. Stay curious, and we'll see you in the next one.